Hi, my name's Annie,
I'm Jericho.
and this is our project for PHYSCI121 that focuses on the cognitive deficits and intellectual functions that are associated with Duchenne muscular dystrophy.
Throughout this course, we have learned about how Duchenne muscular dystrophy is an X-linked genetic disorder that leads to low levels or even a complete absence of dystrophin, a protein responsible for linking intracellular cytoskeleton elements with transmembrane components that connect to the extracellular matrix. With little to no dystrophin in their skeletal muscles, DMD patients experience a significant loss in muscle structure and functioning, ultimately losing ambulation later on in life. The patients often require wheelchairs to maintain mobility, ventilators to maintain breathing function, and eventually become bedridden. They require considerable assistance from others due to their limited mobility, increased fatigue, and feebleness.
While dystrophin plays a key role in mediating interactions within our skeletal muscles, studies have also shown that dystrophin is also present in our central nervous system, helping us to process and output information. Therefore, one might wonder how exactly an absence in dystrophin affects the brain and can lead to cognitive deficits. We hope to go into more detail on how Duchenne muscular dystrophy not only affects patients physically, but also intellectually.
So how does DMD affect intellectual functioning? It was reported that mean IQs of DMD patients are approximately 1 standard deviation below the general population. Specific cognitive deficits were reported in story recall, digit span, and auditory comprehension.
So adding on to the intellectual functions associated with DMD, how does a loss of dystrophin in the central nervous system lead to cognitive deficits? Similar to skeletal muscle structure, studies have shown that an absence of dystrophin most likely leads to an alteration in brain structure. With an alteration in brain structure, this would ultimately lead to an alteration in brain function, which presents as a cognitive deficit that we see in DMD patients.
Within the brain, dystrophin is normally the most present within neurons in the cerebellum, which is responsible for key voluntary functions like walking, balancing, eye movements, and speech. Development of brain pathways in the cerebellum without dystrophin can therefore result in altered brain function, and this was discovered in several studies. The loss of dystrophin is associated with a complex set of physiological and anatomical adaptations that are known contributors to the cognitive deficits in DMD patients. Past studies have indicated functional and morphological abnormalities affected by the absence of dystrophin.
Investigators found a complete absence of dystrophin in cerebral and cerebellar neurons in the DMD patients that were categorized as having intellectual disturbances. Some studies have also indicated disordered CNS architecture, abnormalities in dendrites, a loss of neurons in boys with DMD, EEG abnormalities, and the prevalence of epilepsy being higher in DMD than the general population, in addition to CT and MRI studies indicating brain atrophy. There have been significant evidence to conclude an altered brain structure in DMD patients linked to the loss of dystrophin, characterized by the disease and therefore leading to cognitive deficits. Specifically, the cognitive functions in adult DMD patients are deficient compared to the normal population. Their ability to sequentially process auditory information was reduced in attention and memory. However, cognitive abilities that do not require sequential processing were not impaired.
Dystrophin is a structural protein that connects the extracellular matrix to the cytoskeletal to provide protection against contraction-induced damage in muscle cells, but it is also expressed in neurons within specific brain regions. Aside from affecting the cerebrum and cerebellum of the brain, it has also been found that the lack of dystrophin may affect the hippocampus, which is a brain structure associated with learning and memory formation. DMD boys exhibit non-progressing cognitive dysfunctions with deficits in verbal, short-term, and working memory. The absence of dystrophin results in malformed and dysfunctional synapses that are likely to disturb the precise and coordinated neural network activity crucial to the formation and consolidation of memories in the hippocampus.
The loss of neuronal dystrophin is associated with alterations in cellular metabolism, energy requirements, and redox status, all of which result in the hippocampus neurons being particularly vulnerable to hypoxia insults, contributing to hippocampus dysfunction. Furthermore, a past research study identified inflammatory mediators that are chronically elevated in peripheral tissue and plasma of DMD patients in MDX mice. The key pro-inflammatory cytokines are IL-1 beta, TNF-alpha, IL-6, and they exert neuromodulatory effects on the hippocampus and have been linked to altered capacities for learning and the formation of memory.
Psychological stress can also have a negative impact on hippocampal function, resulting in difficulties in memory retrieval and storage of new memories. This is further complicated by the finding that as the patient's disability and dependence on others increase, activities of daily life, quality of life, and life satisfaction decreases. Their severely restricted behavior repertoire is often accompanied by psychological distress, which can also add on to their impaired hippocampus function.
Throughout this video, we have demonstrated how a loss in dystrophin within the central nervous system can lead to cognitive impairments within DMD patients. We know from taking this course that an absence in dystrophin negatively affects your skeletal muscles, resulting in deteriorations in muscle structure and function and contraction-induced injuries. We were curious to see the correlation between DMD and cognitive impairment, and were able to find that the same absence of dystrophin within the central nervous system can lead to altered structures within the cerebellum, hippocampus, and neuronal networks. And through these changes in brain structure, DMD patients ultimately face cognitive deficits. Studies have shown that there has been a complete absence of dystrophin in cerebral and cerebellar neurons within the DMD patients, abnormalities in dendrites, and brain atrophy through CT and MRI studies. These changes in brain structure on the cellular and macroscopic level have been linked to decreased cognitive functions in DMD patients, not only affecting neurons in the cerebellum. An absence in dystrophin has also been shown to affect key processes in the hippocampus, resulting in dysfunction in verbal, short-term, and working memory.
Alternative explanations to the cognitive impairments seen in DMD patients have been attributed to dystrophin isoforms, particularly to mutations in DP71 and DP140. It was found that an intact DP140 brain isoform was responsible for increased cognitive abilities in DMD boys, but patients with mutations to this dystrophin isoform experienced cognitive deficits. Continued research studying how different dystrophin isoforms present in the brain can contribute to cognitive abilities is an ongoing area of study that could be informative in understanding cognitive deficits in DMD boys. But a common theme is still present in the explanation of decreased cognitive function in DMD patients: the lack of dystrophin.